Okay, in this second video for lesson 7.2, we're going to focus on calculating the value of equilibrium constants when we do not know all of the concentrations of our reactants and products at equilibrium. So in a Rice table, we write down the reaction, we write down the initial concentrations, we write down the change, that's what the C stands for, change in concentration, and then we write down the equilibrium concentration. So that's what Rice stands for. The reaction, initial concentrations of each reactant and product, change in concentration, and equilibrium concentration. Let's see how they work. Here we have a sample problem. This is on your paper. We have a closed system that initially contains 1 times 10 to the minus third molar hydrogen gas and 2 times 10 to the minus third molar iodine gas. It's at 448 degrees Celsius. It's allowed to reach equilibrium. So it starts out initially containing this amount, and then they are going to react according to this reaction, and equilibrium is reached. Analysis of the equilibrium mixture shows that the concentration of the product is 1.87 times 10 to the minus 3. So we need to calculate K at 448 for the reaction taking place. And at equilibrium, remember, we're going to have some concentration of product and some of reactants, and it will look like the concentrations are not changing because the rate of the forward reaction is the same as the rate of the reverse reaction. So the first thing we do is write down what we know. So these are the categories, what I'm circling now, of our Rice table. So we have a row for reaction, where we write down our reactants and our products. And I put our reaction up here, just so we could look at it. Actually, I've written the reaction up here and also here and corrected it. So on your table, you're going to want to put a 2 in front of this HI for the reaction because that is the coefficient. So then in our next row, we have the initial concentrations. So our problem said initially we had 1 times 10 to the minus 3 molar of H2. It said we had 2 times 10 to the minus 3 molar of I2. And since it's initial, it told us that we just put these into a vessel and they haven't reacted yet. So our initial concentration of product was 0. Now we have here a row for change, and we have not put anything in it because we have not yet calculated how each of these are going to change. And then our final row is at equilibrium, and the problem did tell us that at equilibrium our concentration of HI was 1.87 times 10 to the minus third molar, so we write that down. Now we are in a position to write down what changed as the reaction progressed to equilibrium. And this is where the equation can be very helpful, because we have H2 plus I2 makes 2HI. This is an I. And our coefficients in this equation are 1H2 plus 1I2, chemists never write the ones, makes 2I2. So that means we have 1 of H2, and I'm going to just say that's X. Okay, because it's just one thing. So 1, and I have another equal amount, another 1, so another 1 mole, which I'm going to call X. And after the products are made, I have 2X, because if I start with 1 mole of H2, I make 2 moles of HI. So the relationship of HI to H2 is 2 to 1, which is why I put this, whatever product we make here, it's going to be twice as much as the moles of H2 that we started with, and twice as much as the moles of I2. So I'm representing this by a 2 times the X that is for each of these moles. Okay. And I think we were told in our problem, I'm going to have to pause, we were told in our problem that at equilibrium we had 1.87 times 10 to the minus 3 molar of HI. So that's our change. We went from 0 products to 1.87 times 10 to the minus 3 at equilibrium. So the change for the HI was from 0 to 1.87. It's a positive change, 1.87 times 10 to the minus 3. And I'm just putting my x and 2x. So now what we're going to do is think about, even though we were not told in the problem, oopsies, we were not told how much H2 and I2 changed, but we're going to figure that out. Because if the increase in HI is twice as much as the decrease as the number of moles of I2 that were used up, this is a 2-to-1 relationship, then if I increased my HI by 1.87, my I2 had to decrease by half of that. That's why I have 2x, this is 1x, so the change here is going to be, these x's really belong down here in the change category. When we do another problem, we'll write them there. So if this is 2x of change, then this had to decrease by 1x, or half of that. And minus 9.35 times 10 to the minus 4 is 1.87 times 10 to the minus 3 divided by 2. And this had to decrease by half of that as well, or the same amount as I2, because the relationships between H2 and I2 are stoichiometrically equivalent. 1 mole of this and 1 mole of this. So these two decreased by minus 9 and the minus shows the decrease, that's what that means. They decreased by 9.35 times 10 to the minus 4 each. In the next slide, we're going to calculate what the concentration of these two are at equilibrium. So, if we start with 2 times 10 to the minus 3 of I2, and remember this is our reaction, H2 plus I2 goes to 2HI, and we decrease by this much, 2 times 10 to the minus 3, minus 9.35 times 10 to the minus 4 is 1.065 times 10 to the minus 3. You can work it out yourself. 2.00 times 10 to the minus 3, put it in your calculator, minus 9.35 times 10 to the minus 4 gives you this number. Over here we started with slightly less H2, subtract this much and you get this amount. So now we know our concentrations at equilibrium of each substance in our reaction. Now we can calculate the equilibrium constant by plugging these values in to our equilibrium constant expression. So for this reaction, this is our equilibrium constant expression. HI to the second power, because of this coefficient of 2, divided by the concentration of H2 and the concentration of I2. I think these were all gases, so they're all included in here. I'll put that up here. Gas, gas, gas. So what we're going to do now is substitute in the values for each of these. So our concentration of HI at equilibrium from the previous slide is 1.87 times 10 to the minus 3, and we're going to square that because of this 2. Our H2 concentration is 6.5 times 10 to the minus 5th, I believe. And our I2 concentration is 1.065 times 10 to the minus 3. Now we can square this, then divide it by this, and divide it by this. So I've simplified this expression. 1.87 times 10 to the minus 3 squared is 3.4969 times 10 to the minus 6th. If you multiply 6.5 times 1.065, you get 6.9225. 10 to the minus 5th times 10 to the minus 3rd is 10 to the minus 8th. Now I can simplify this expression, and I get 0.505 times 10 squared, which is 50.5. So this is the value of our equilibrium constant, and we were able to calculate that, even though we were given limited information, by plugging what we were given into a table that allowed us to calculate the change and finally the concentrations at equilibrium. So we're going to use those Rice tables a lot. Let's do another problem. Okay, so in this problem, we're going to read it and see what we need to do. It says talks about what we did in a previous exercise between N2O4 and NO2. So then it says, when 9.2 grams of frozen N2O4 is added to a 0.5 liter reaction vessel, and the vessel is heated to 400 Kelvin, and then allowed to come to equilibrium, the concentration of N2O4 is determined to be 0.057 molar. Given this information, what is the value of K for the reaction N2O4 going to 2NO2? Okay, so the first thing, we're asked about equilibrium and we're asked to calculate K. So we're going to create a Rice table. We're going to have a reaction, an initial concentration, a change in concentration, and our concentration at equilibrium. And we can put our reaction right here. Let's do it in purple. We have N2O4 going to 2NO2. Okay. And what else do we know? Well, we know that at equilibrium, when it comes to equilibrium, the concentration of N2O4 is 0.057 molar. So this is the concentration at equilibrium. So for N2O4, our equilibrium concentration is 0.057 molar. Do we know anything else? Well, let's see. We know we started with 9.2 grams of frozen N2O4, and it was in 0.50 liter reaction vessel. So we can calculate the initial molarity of our N2O4. We're going to do that right here. I'm going to make this smaller, actually. Hold on. Okay, so we're going to just calculate our initial concentration. We have 9.2 grams of N2O4. We need to figure out how many moles that is. So 1 mole of N2O4, 2 times 14 for N, and 4 times 16 for O. So that's 28 plus 32, 64. So we have about 8 plus 4 is 2. I hope I'm not making a mistake. So I think that's 92 grams in a mole of N2O4. I need my calculator. Although this problem is written so you could do without a calculator, so let's do that. We have 9.2 divided by 92, so that's going to be 0.1 moles. Because on the whatever test we're taking, the AP, there's part where you can't use the calculator. And then we're going to have to get our molarity, we have 0.1 moles over, here it was 0.5 liters. So that's 1 over 5, which is 0.2, right? I'm going to double check it. Yes, so 0.1 over 0.5 is the same as 1 over 5, which is 1/5, which is equal to 0.2 molar. Okay, so now we know our molarity. I'm going to shrink this. Oh, does it let me do that? Oh, I'll just move it up here then. Bye-bye. Here's our molarity down here. I'm going to make my table big over here if I hopefully can. Yay! Okay, so we're going to fill in, this was our initial molarity of N2O4, 0.2 molar. Now, here, if we look at our stoichiometry of our reaction, we have 1 mole of N2O4 going to 2 moles of NO2. So our change is going to be, if this is minus x, this decreases by 1 mole. This will increase by 2x. Okay, that's important. So if our change here, we went from 0.2 to 0.057 at equilibrium. So we can actually calculate a change there. 0.2 minus 0.057. So 0.2 minus 0.057 means that we had a change of 0.143. 0.143 molar. That was our change, which means that's our x. Okay, that's what we decreased by. So this side is going to increase by double that because the stoichiometry is 1 to 2. So we take 0.143 and we double it on this side, meaning that this is going to increase by 2 times 0.143, 2 times 0.143, which is 0.286. Now our initial concentration of NO2 here was 0 because we started by just putting frozen N2O4 in there. So this is 0. And if you add 0.286 to 0, you get 0.286. So now we have an equilibrium concentration of NO2 and of N2O4. Our equilibrium constant expression, Kc, is equal to the concentration of NO2 at equilibrium squared, because of this 2, divided by the 1 N2O4, and these are both gases over here once they became unfrozen. So now I can substitute. Just going to put a line here. Kc equals 0.286 squared over 0.057. So Kc equals 1.43. So the correct answer is D. Okay, let's work another sample problem. We have the gaseous compound bromine monochloride, decomposes at high temperature in a sealed container. This is our reaction to bromine monochlorides going to bromine gas plus chlorine gas. Initially, the vessel is charged at 500, and charged means filled, at 500 Kelvin with bromine monochloride gas at a partial pressure of 0.5 atmospheres. At equilibrium, the bromine monochloride partial pressure is 0.04 atmospheres. Calculate the value of Kp at 500 Kelvin. Okay, so remember, atmospheres pressure is proportional to concentration, so here we're just going to work with pressures and calculate our equilibrium pressure constant. And we're going to create a Rice table because we're given the equilibrium concentration here, and we're given an initial concentration, but not everything that we need to know. So we have reaction, initial concentrations, change, and equilibrium concentration. Our reaction is 2 BrCl going to Br2 gas plus Cl2. So we're going to have 3 columns. Okay, what else can we fill in? Our initial pressure of bromine monochloride is 0.5 atmospheres. So this is 0.500 atmospheres. At equilibrium, the bromine monochloride partial pressure is 0.040. So that's at equilibrium, it's 0.040 atmospheres. Calculate the value of Kp, and they keep telling you it's 500 Kelvin because equilibriums are different at different temperatures, so the temperature had to stay the same, or we couldn't do this. So let's look at what the value of our change is, first of all, stoichiometrically. If we have 2 of these decomposing, for every 2 of these that decompose, 2 moles, we get 1 mole of this and 1 mole of this. So for every minus 2x here, we get plus x here and plus x here. Now we can calculate what our change is here because we know our initial and our final, our equilibrium. 0.5 minus 0.04 means that our change is 0.46 atmospheres. 0.46 atmospheres. Okay, so if that's 2x, then x would be half of that. 0.46 divided by 2 is 0.23. So again, if this decreases by 0.46 atmospheres, that means since it's 2 to 1 here, this would increase by half of that, and this would increase by half of that. So these are our changes. Now our initial concentrations of each of these are 0 because we only started with bromine monochloride. So 0 plus 0.23 is 0.23, 0 plus 0.23 is 0.23. Now we're in a position to calculate the value of Kp that we were asked to do. Let's make this a little smaller. Okay. Let's do a different color, purple. Okay, so Kp for this reaction equals our products, Br2 times Cl2, the pressures, over bromine monochloride squared. We'll substitute. This is 0.23 times 0.23 atmospheres, and they're all in atmospheres. It's important that all the units be the same. And our bromine monochloride concentration at equilibrium is 0.40. 0.040 squared. So now I'm going to simplify that. So that simplifies to 0.0529 over 0.0016. If I divide those two things, I get a value of 33.06, which I'll round to 33.1. So that is the value of Kp at 500 Kelvin for this reaction. And I think that is it.